Hey y'all, it's Mr. Boyden back at it again. Today we're going to start our unit on bivariate data. Bivariate just means two variables. And so the first thing we're going to look at with that is scatter plots and correlation within the scatter plots. So we're going to kind of set the table here at the beginning of the video and lay out the 7 things we're going to talk about today. Let's just run through them really quickly and then we'll get into some examples as we go. So first things first, response variable and explanatory variable. I think I introduced these a little bit earlier as well. Okay, so response variable, specifically, this is the thing that you measure. Okay, sometimes I've seen my students get kind of confused on this and they're like, which one is which? Or I thought this was explanatory. If you're not measuring an outcome, then it's not the response variable. You're measuring the response of something, maybe the response to a treatment, for example. Okay, in terms of like math, it's an output, so outcome, or like an output variable, if we're talking about like a function. And it is similar to the idea of a dependent variable in science. Okay, so on the flip side of that coin, an explanatory variable, that's like the input. So I'm going to write that down here too. So it's like an input. And so that's the thing that may predict what happens in the response variable. It's like an input, or it's like the independent variable. Okay. It's also, sometimes people will call this the manipulated variable. It's in an experiment, it's the thing that we are controlling, and then we measure the response. So that's how those two come into play. Okay, scatter plots, guys, I'm pretty sure you've all seen a scatter plot before, especially if you're in high school. Usually you learn about these in elementary school for the first time. It looks like a bunch of dots. It's important that you know that we are talking about two variables and we have a scatter plot. That's why normally you have some variable on the x and on the y-axis, and you have some dots on there that represent each of those variables for one person or for one trial or something like that. Okay. When we're asked to describe a scatter plot, there's typically 4 things they're looking for. And these are, once you learn these are super easy to score well on. Okay, so the first thing is the direction. Is it positive, negative, or none? Now, they use the word association here. If you want to make it even a little easier on yourself, consider that to be a slope. So like in this example that I just made up above here, I have a positive slope. Okay. The next thing we need to know is the form. Is it linear or not? Now guys, if it's not linear, it might be curved. For example, some things are curved. It could, maybe it has no pattern at all, and we would say, I don't really know if it's linear. Okay. For C, the third thing, the strength, is it a strong or weak association? We'll talk a little bit more about that in a minute. One of the things that's frustrating is there's not like a clear boundary between strong and weak, like, oh, like a 0.7 is strong, but a 0.6 is weak. There's nothing like that. It's one of those sort of ambiguous terms. So we'll do some examples here in just a minute to give you a better feel for that. And then we look for any unusual features, like is there an outlier? Now an outlier means something a little bit different on a scatter plot. An outlier would be like if there was, on the one that I have right here, if there was a dot down here. Because you've got a pretty strong upward trend, and then, whoa, what's going on down here? There's a dot that really doesn't fit the pattern. So that's what we mean when we say an outlier in this case. Now, when we say an outlier on a scatter plot, we do specifically mean just a point that really doesn't fit the pattern. We're not talking about a formal definition of an outlier here. Okay, so those are the 4 things. It's pretty common that there's a question that asks about that on an AP exam at some point, so that's good to know. All right, next thing we need to talk about correlation. When we say correlation, and let me color code this so it kind of stands out just a little bit to you. When we say correlation, we really are talking about 2 things. We're talking about is it positive or negative, and is it strong or weak? And that's how we typically describe correlation, is with those terms. Okay, one from each of those pairs. So we could have like a positive, weak correlation, for example. Okay, and we'll see some more examples of that. For your notes, please make sure you have down that when we say correlation, we're talking about the letter R. Okay, and that's going to come up more a little bit later too. A little bit later in this video, we're going to look at examples of correlation versus causation. So we'll talk about that when we get there, and at the end of the video, we'll talk about the limitations of correlation and a couple of things that you need to know, because it's great to know what correlation is, but it's also important to know what correlation is not, so that we can use it responsibly. All right, so let's look at some examples of correlation, just visually. So I have 8 examples on the screen now, And there's that R. Now, they've written it as a capital R. I do want to let you know that typically we use a lowercase letter r. This is I took it off the internet and it's an older image, so they, for whatever reason, the programming had a capital R. But you use lowercase, please. Okay, and so let's start with the one way over here on the right. I'm talking about this one. And this one over here, the reason it's a 1, that's a perfect correlation, is because if you drew a line, it would hit literally every point. It would be touching every single point. Okay, the next one, so one to the left, this one's a 0.98. That is still definitely a strong positive. So I'm going to go strong positive. R equals 1 is like, first of all, that basically never happens in the real world. So it's like a perfect positive, but it would be strong as well. 0.69, it's kind of strong. Depends on who you ask, if this is strong or weak. It doesn't really seem weak. There's definitely a linear trend going on here. It is positive. And this last one is positive too. Okay, and so notice all of these values of R are positive numbers. And that's what we mean when we say it's positive. And each of these, the pattern is an up and to the right, a positive slope type of deal. Now, what about this second row down here? These are all negative. Now, but what about this first one though? It's not really clear that it's negative. So there's an equation or an algorithm that's being run in a computer that's popping out a negative number. But the fact that that's a 0.08, it's indicating like, technically it's a negative trend, but like there's not really much of a trend there. And we can see that in the scatter plot. There really isn't much of a trend here. And how would you put it? Would you put a line like this, like that? I don't know. I'm not really sure. Okay. What about the next one? This one's a little bit stronger trend. I don't know if you'd quite call it strong. 0.64 is kind of that borderline. It's kind of in between strong and weak. And so to write a test question, we'd have to be a little bit more clear, a little bit less ambiguous. Okay, here we have a strong negative. So you know what, I should have annotated this. This is technically a weak positive. This is a weak negative, although in the real world, we'd almost say no correlation. It's so close to 0. And then over here with this one, we have a strong negative correlation because it's going down. And then the last one, basically a perfect negative correlation. All right, now let's learn how to make a scatter plot on the calculator. So we'll deal with a minute with the questions up above, but let's go down and read the context. Each member of a small statistics class ran a 40-yard sprint, then did a long jump with a running start. The table below shows the sprint time in seconds and the long jump distance in inches. And so here are the data. And we're going to make a scatter plot of the data. And the objective here is I want to make sure you know how to do that in your calculator. So up above, we want to say which variable is explanatory, which one is response. Are we manipulating one and measuring the other? Sprint time and long distance. Does sprint time determine your long distance jump? Does long distance jump determine your sprint time? It's not really clear on this one. So this one could go either way. So I put the question there so we'd have a chance to think about it. And this one, it doesn't really matter. What I'm going to do is I'm going to let the column on the left go in as my x values and the column on the right go in as my y values. All right. So take note of those values. If you have a TI Inspire calculator, you'll want to have that ready now, because now I'm going to show you how to use that calculator to generate a scatter plot. All right, to do so, we're going to, well, they asked us to press the menu, so I got to press the menu. I'm going to add a list/spreadsheet. Always remember to label it. So I'm going to call sprint the first one. And then I'm going to call distance, or maybe we'll do sprint, we'll do jump for this one. You can call them whatever you want. It doesn't actually matter, but you have to have something descriptive there. And then we're going to enter in the values. So 5.41 and 171, that represents the first person. Okay, and guys, I think you could probably fill in the values from there. So I'm gonna, I encourage you to pause the video and take a moment. You may need to rewind to go back and get those values. And then I'm gonna stop recording for a minute and input all the values. And then when you hit play, this will all autofill for you. All right, so there's all my values. Now we wanna make a scatter plot. So what we're gonna do is come over here to Control and add a page. That's the dock button up here. Remember, that'll add a page. The page we want to do is data and statistics. Anytime you're trying to visualize your data, that's what you're going to do. I know it feels like you're going to hit graphs, but we're not graphing, we're visualizing data and statistics. And then we had decided that we were going to put, I think I had said the sprint. Yeah, the sprint down here for X. And come over here to the right. Now, guys, if you're using one of those yellow TI inspires, it's going to look like there's nothing here to click on, but I promise you there is. Hover up here and just click. Trust me, it'll prompt you to pick one of these. I know that's weird programming, but that's what they did for some reason. And so there it is. Okay, now we need to describe the graph, so I think I'll do a snip of the graph. So, first of all, does it look linear? Yeah, pretty much. It's not curved is what I'm looking for, so it is linear. Awesome. What else can we say about it? Is the correlation strong or weak? Is it a clearly defined pattern? Yeah, that's a definite clear pattern. I'm going to call that a strong correlation. We'll find the correlation coefficient in a minute. We'll see if that backs this up. Okay, positive or negative? It's going down in the right, so that is a negative slope, and it has no unusual features. Okay, and so I'm not writing it as a complete sentence, but that is a complete description of this graph right now. So let's jump back over to the calculator for a minute and talk about a couple other things that we have the ability to do. First thing is you can hover over a point, and each point represents one person. Okay, so this person did their sprint in 5.05 and then they jumped 184, for example, is what that's saying. There's other stuff you can do though. Now remember, in this calculator, most of the stuff that happens that's good for us happens after we hit the menu button. Let's go play with that for just a second. Let's go to menu. Let's see what happens in Analyze. Now we have something in here called Regression, and we can show a linear regression. 1 and 2 do the exact same thing, okay? And the first one says mx plus b, so that probably reminds us of our algebra class, maybe from 8th or 9th grade, something like that. In statistics, for some reason, they like to use a plus bx. And so that's the one I'm going to pick today. If you really insist on using mx plus b, totally fine, okay? But statisticians are, I don't know, a little different, so they chose to use this. And so that's going to give me the least squares regression line. And so now I have the equation. I also want to show you another graph type that you can add. So let's go back in, and let's go to Analyze. And I want you to go down to Residual. So I'm going to slow down for just a second. So at Menu, Analyze, and then Residuals. And we're going to look at the residual plot. And so what I'd like you to do now is I'd like you to pause the video, and without looking it up, try to figure out what is a residual plot and what does it tell us about the graph. So you have your actual scatter plot above and your residual plot below. So pause and see if you can figure out how these two graphs relate. All right, did you figure it out? So if you look at the residual plot, it has all of the same points, but it's not showing this vertical axis. It's showing residual instead of the jump on the vertical. But notice, for example, like, see how this point right here is just barely above the line, or it's kind of on the line? This point is on the line. See how this point is just barely above? This point is just barely above. This point is below. This point is below. And so on and so forth all the way down. It's almost like we took that line up here and we just flattened it out, and now that shows us the residual. And guys, that's what a residual is. It just tells us if we're above or below the line and by how much. So for example, you see how on this one the y value is 22.61? What that's indicating is that this point is 22.61 units above the line. So that's saying this distance up here from here down to the line is 22.61. What happens when it's below? You see how that y value now is a negative number? The fact that it's negative indicates that that point is below the line, meaning this person didn't jump as far as the line predicted that they would. That's an important thing that I really haven't said yet, is that that line is a prediction. So if there was a student and we knew their jump or their sprint, we could make a prediction about the thing we didn't know about. Okay? All right. Let's take our mouse, use this mouse pad over here, go back to the top, to 1.1, and I want to show you another command that you can do in here. Okay, and so go to like cell C1. From C1, let's go to the menu, and let's go do some statistics. We're going to look at a stat calculation, and the one we're going to do is two variable statistics. No, let's do linear regression. We did linear regression a minute ago. Let's do the table version. That's the exact same command we just used on the graph a minute ago. So linear regression, we are going to have to tell it what we mean. So I had sprint as my x value and y as my jump value. And we're going to leave everything else alone. So sprint and jump for x and y, and then hit OK. Now, you'll notice right away, I hope, that these two values, the 414 and the negative 45.7, those are the same values that we saw on the graph. Let me go back to the graph. And there they are, right here and right there. So now it's just showing us in table format, and that's our y-intercept and our slope. And that's another piece of evidence that it was a negative association. We found a negative slope. This tells us more, though. This tells us R. It says R is negative 0.838 or 0.84. That's a good piece of evidence because that's pretty darn close to 1. That's telling us that it's a negative, strong correlation. That's awesome. Okay. They also give us R squared, which we're going to learn about in the next lesson. So we'll talk about that when we get to it. All right. Now, let's talk about correlation versus causation. And guys, the deal is our brains naturally want things to be causal. If things have a causal relationship, that means that if we manipulate one factor, it will have an intended effect on another factor. And that, I think, probably in terms of our psychology is probably pretty comforting, that like, hey, if I can change this, it'll change that other thing, and then I have control, I have power. Okay, but that's just simply not often the case. And this is a dangerous thing that we do sometimes with data. We'll look at pieces of data and say, oh, well, therefore I need to make this conclusion. Let's look at some examples. So for example, and these are all true, by the way. All the ones that I'm about to show you, these are not made up correlations. These are real, true things. Okay, there is a strong correlation between the number of shark attacks and the amount of ice cream consumed. That's for a given month, by the way. So in a month where there's a lot of shark attacks, there's also a lot of ice cream that's consumed. So sometimes people will hear that, they'll say, oh, you know, when we're eating a lot of ice cream, we're more likely to get attacked by sharks. And so that probably means that sharks know we were eating ice cream and they like ice cream, so they're going to eat us. So what we could do is we could just not eat ice cream and we'll be less likely to get attacked by a shark. No. No. Okay, there's a confounding variable here. And the confounding variable is the temperature, or the air temperature. Because when it's warm, people are more likely to go swimming at the beach where there are sharks. And when it's warm, people are more likely to want to eat ice cream to cool off. Okay, you go to the water to cool off, you eat ice cream to cool off. In the winter, not a lot of people swimming in the water and not a lot of people eating ice cream. Now, yeah, people still swim in the winter and people still eat ice cream in the winter, but usually we eat a lot more in the summer. So that's a true correlation. But it's not as if shark attacks cause ice cream. It's not like, oh, I get bit by a shark and then I want to go eat ice cream. No, that's not what's causing the correlation. Okay, here's another one that may be more relevant to us. There is a strong correlation between the number of IB exams that a student takes and their performance in college. And that's a positive correlation, meaning that students who take more IB exams on average have a better performance in college. So why is that? And what should we do about it? Well, what I have heard some people say, and they do the same thing with AP exams, is they say, well, students who take more AP exams do better in college, so what we should do is make sure all of our students take lots and lots and lots of AP exams. Now, is it possible that AP exams and IB exams in some way help prepare you for college? Yeah, that's definitely possible. It's definitely, it's not going to make you less likely to be successful, certainly, and having some test prep stuff sure could help. However, we need to also be open to the idea that it's also possible that people who are really, really good students, the ones who are going to do well in college anyway, are also very likely to challenge themselves by taking AP and IB courses. In the research they've done on this, there's no reason to think that it's a causal relationship, okay? But it's definitely a correlation. We have to be careful, though, because if we say, oh, well, that means we should just have everybody take lots of exams, that becomes very expensive and it could put people through a lot of anxiety and it removes their choice. And maybe it's a good thing, maybe it's not, but we should be careful. One thing I don't think I said yet, I've been saying the word, I didn't say anything about the word though. This word right here, that is not casual. Okay, so I don't know if your brain saw that. A lot of people, if they don't know that word, they see it and they go, oh, it's casual, Mr. Boyden misspelled it. I didn't. It's causal, as in causation, okay, or cause and effect. Okay, so that we call that a causal relationship. Okay. Here's another one, and this is a real one as well. There is a correlation between household income and GPA of children in the household. So basically what this is saying is if you come from a household that has a higher income, you are on average more likely to have a higher GPA as compared to someone who comes from a lower income household. And if you think about it, that kind of makes sense. There's potentially quite a bit of privilege that comes with your income or your socioeconomic status. And so you have some advantages or some disadvantages depending on that. Okay. It doesn't, and by the way, that's not saying for you as an individual that's true. I mean, there are plenty of students that I've seen that come from very well-to-do families who've been terrible students, and I've seen some outstanding students who come from a very disadvantaged background. This is just saying on average, as a general rule, maybe there's lots of reasons for this. Maybe if you have a higher income, your parents are willing to hire tutors for you and things like this. So. And maybe if you're from a lower income, your family can't afford a babysitter and you end up babysitting for free a lot, so you can't focus on school. So lots of reasons why that could be. So let's think about the following question though. If a low income household wins the lottery, do we expect the GPA of their kids to go up? Maybe, maybe not. It's hard to say. Some people say, well, yeah, because more money means more grades. Maybe. It depends on why they weren't getting good grades. I mean, and it depends on how they're sometimes it could be like a household culture. We don't really know. Actually, it's kind of a fun thing to look into on your own. There's like the lottery winner's curse, where the suicide rate is actually a lot higher for people in the lottery. And that's kind of a weird statistic, but way higher than the general population. So something, if you want to look into that, you could look into the lottery curse if you were curious. All right. Guys, those correlations occur naturally all the time. And it's kind of like this. If you have enough data, you're going to be able to find a pattern in it somewhere. And it could be a false pattern. It could be a causal pattern. We don't know. And it's not that you should assume things are not causal, but just be careful and aware that you should not be assuming things are unless there's a good reason to think so. So I want to show you some more examples of why you should be cautious. And these are all true, by the way. Okay. So here's two variables that have a strong correlation. The number of people who drowned while in a swimming pool and the amount of electricity or the power generated by U.S. nuclear power plants. So there is at least data-wise a connection between drowning in a swimming pool and having power plants. Now, are swimming pools causing us, are dying people causing us to make more power plants? Are more power plants causing us to drown? No, there's no cause here at all. It's a strong correlation though, 0.9, so kind of interesting. Okay, what about the next one? Per capita consumption of chicken, that just means per person, so the amount of chicken people eat, and the total U.S. crude oil imports. Those tend to go together. So why would that be? Chicken, if we eat chicken, that means we need oil. If we use oil, that means we need chicken. No, there's a confounding variable here. Okay, the confounding variable is population, possibly. Population and economic recessions. You could imagine a time period, for example, guys, we hit a recession here in 2008, and then it went way down in 2009. People had less money, and so people probably were not buying chicken. Chicken kind of became, for a lot of families, a luxury item that was really hard to afford. So if you're buying less chicken, and people also were not taking road trips or driving as much, and many people lost their jobs, so they had nowhere to drive to, and so that was going down as well, and they just happened to go down at the same time. So population growth would drive it up, but then an economic recession would bring it back down. So it's not like chicken is causing oil. I mean, they just happen to go together. Okay, another one's kind of interesting. The divorce rate in Maine correlates with the per capita consumption of margarine. So what is this saying? That when we eat less margarine, there's less... So wait, is margarine causing divorce? Does that mean if we would just get rid of margarine, there'd be no divorce? No, it doesn't say anything like that. This is one of those, it's just possibly a coincidence. Now, could there be more? Sure, but we have no reason to believe that margarine is causing a divorce rate. What's bizarre, look how high that correlation coefficient is. That's crazy, 0.99. Oh my goodness, that is a strong one. By the way, what I'm trying to warn you against is, seeing something like this doesn't mean you should make a decision. Like, for example, if your parents are still married, you should not run to them after this video and say, we have to throw away the margarine. No, maybe for other reasons you should throw away your margarine, but not for this one, okay? That's not what this is saying. This is saying, like, this likely coincidentally is just two variables that go together. So I don't know what that's about, actually. It might just be that they both happen to drop over time. Maybe less people are getting married, so there's less divorce. And we've certainly, decreased our margarine consumption in this country after we've learned about some health effects. So it could be probably a total coincidence. Here's another one's kind of bizarre. The number of people who drowned by falling into a pool correlates with the films Nicolas Cage appeared in. So when Nicolas Cage makes more movies, there's more people falling into pools. I don't know. Is that a coincidence? Who knows? Maybe that's causal. I'm not sure. Depends on if you like Nick Cage or not. I don't know. In any event, it's kind of just a silly one. Here's another one that's true and not silly. So the percentage of people who wear seatbelts correlating to the number of astronauts who die in spacecraft. So check this out. In the 1980s, the seatbelt usage wasn't super high. In the 90s, look at this blue bar, it goes way up. And part of that was just due to public awareness. Part of it was due to laws. Like in our state, there was the campaign called Click It or Ticket, where they'd pull you over and give you a ticket if you didn't wear a seatbelt. And so that went way up. Now, look at the orange, the astronaut deaths. We had, in the teens, the number of astronauts that were killed in the 80s. And it looks like we had maybe one in the 90s, not very many. So if you are unaware of the difference between correlation and causation, you might be tempted to think that the fact that we're wearing seatbelts in our cars has caused the number of astronauts who die to go down. And guys, that's just crazy. There's no way that's true. That by me putting my seatbelt on in the car, the astronauts are safer. No. It's a coincidence. Okay, and potentially, there were some notable disasters in the 80s where a bunch of people died at once. So that's part of it, of course. And then maybe we happen to not have those in the 90s. Maybe there was a change in the spaceflight world, and so that changed. Or it could be just chance. That could happen too. Last thing we need to talk about today is the limitations of correlation, which is R. Okay, the first thing is it's not very resistant. Here's what that means. It basically is saying that if you have a scatter plot that's like a strong scatter plot, and let's say that R is like 0.93, and you have one crazy outlier down here, that's going to totally throw off the correlation. The new correlation is going to be like 0.7. So it's the resistance. Remember, that's that idea that an extreme value, so if something is resistant, an extreme value doesn't change that measure very much. But now by saying this is not very resistant, what we're saying is one extreme value, one outlier, can really throw off that measure. Okay. R is only useful in describing relationships which are linear. Now in this course, we really only study relationships that are linear. At the end of the year, we'll talk about how to transform non-linear data to make them linear, but that's another story for another day. Okay, but it's not useful for like quadratic or exponential or logarithmic relationships. And the last thing is correlation tells you nothing about the shape of a distribution. So if a curve would be a better fit, the correlation is not going to tell you that. Let me draw you an example of what that could look like. So you could have something, let's do a little better job than that though. You could have data that look like this. Okay, now I hope you can see that that's curved. And I tried to make it a really clear pattern, so that is curved. A computer model will come in here and it'll put, I should draw a better one than that. It'll come in and it'll draw a line through like that. And the correlation will be really high. It'll be like 0.9 because all of those points are quite close to the line. And so you could make the mistake of saying, R equals 0.9. So yeah, cool, it's linear. It's a strong positive correlation. When actually by visualizing the data, by looking at the graph, you can tell that, whoa, wait a minute. Those data are not linear. Okay, and so we got to be careful about that. That's something that you need to be aware of, that limitation of correlation. People, thanks for listening this long. I hope you enjoyed the video and that you'll enjoy the next one, and I'll see you next time.